All right. So, kind of pick up where we left off. Kind of switch gears a little bit from what we've been looking at. We're still going to be dealing with probabilities, but talking about them in a slightly different context. Just kind of where we're going, just as a roadmap. So we should be kind of doing some discrete random variable stuff today, finishing it up on Monday. So Monday should be the last kind of new material. Then on next Wednesday, I'll do some review from some of those practice exams, which I think I showed you where those are at last class, under the files tab on Canvas. And then the following Monday, so it'll be October 3rd, we'll have an in-class exam. Okay, so I'll get an announcement up on Canvas that kind of reaffirms that. I believe the syllabus originally had next Wednesday as our exam date. I'm going to push it forward one class period so we can make sure we get some review in. Okay. You currently have kind of the Connect and Excel homework. Those will both be due next week. I think I have the end of day Thursday for the Connect because it was assigned a little bit earlier, and then the Excel will be kind of due the next day. Right. I'll also put up an announcement after class. My office hours tomorrow usually are 2 to 4. We're going to switch them around a little bit. So if you're planning on coming in tomorrow, I'll be here from 1:15 to 3:15 instead. I'll have those open for office hours. I've got a meeting I have to go to that is at 3:30. So I want to make sure that I kind of move those office hours a little bit earlier so we still get the full 2 hours that I usually would have tomorrow. Okay. So you'll see that announcement pop up about office hours and the exam date change. Other than that, any questions for me before we jump into things here today? Okay. All right. So I think we can get to some interesting stuff here today. So we're going to start out. I'll go pretty quick through the initial stuff because it's going to be really similar to stuff we've already done. It's just put in a slightly different context, right? So we've been talking about kind of these experimental outcome spaces. We've got some experiment, whether that's flipping a coin or whatever it is, and we don't know what the outcome is ahead of time. So we're going to deal with these random variables that we don't know what the numerical response is going to be before we run this experiment. Right? Now there could be 2 different outcomes. There could be 50 different outcomes. There could be an infinite number of possible outcomes. Right? So the ones that we're going to deal with prior to this first exam are discrete random variables. So just like our normal variables where we've already seen the recorded responses, right? The experiment has already been ran, right? This is going to be just a data set. We can have discrete and continuous variables. We can have discrete and continuous random variables. Right? That's going to look no different than what we've already kind of discussed, right? So it's going to, sorry, I jumped the gun a little bit. The way that we're going to notate these random variables is just with a capital X, right? So, in practice, this capital X will be whatever we're interested in. Right, so this might be the return rate on an investment. This might be, if I select someone at random, the number of children in the household. Right, X is just going to be what we're interested in, the event we're interested in. Okay, we're then going to think about whatever this event we're interested in is. We can see all these different outcomes. So we'll kind of call those lowercase x, and x subscript 1 would be the first possible outcome we could see. X subscript 2, the second possible outcome. So I'm thinking about an example here where you guys select a family at random, ask how many children in their household. X1 would be 0, X2 would be 1 child, X2 would be 2 children, and so on and so forth. Or X3, sorry, I think I said the same thing both. Right? You get the idea, right? All these possible outcomes that we can see. Okay? So we're just going to deal with discrete random variables before the exams. We'll focus on those, and I'll probably kind of like just gloss over the continuous random variable slide for right now because we'll come back to that after exam 1. But usually with these, we're going to have some finite number of responses, and generally they're pretty small, right? So even with the number of kids in the household, 0 through 20 or something like that. So a pretty small number of responses. We've already kind of seen this slide where I showed you on a number line. This means we can see the integer values. We can't see, a decimal value in between. Okay? Continuous variables would just be the opposite. We've already seen this before. Once again, this is just a review, right? And we can see the decimal values, right? So continuous random variables become a little bit more difficult because there's an infinite number of possible outcomes we can see. So it gets a little bit harder to assign the probabilities there. But for discrete random variables, we can actually, this isn't too bad. Okay? So, right, if I think about what variables or what these random variable X might look like, family size, I've kind of already mentioned, is discrete. maybe the distance from the nearest grocery store. Well, I can measure distance to whatever fraction I want, continuous. And then one thing that we'll do, and I don't know, we probably won't really hammer on this, but this will kind of pop up again later on in the semester, is at this point when we start thinking about random variables or some experiment that we're running where we don't know the outcome, we're going to kind of change qualitative variables into quantitative. So here, right, if I had some survey data about pet ownership, and you either don't have a pet, you only have a dog, you only have a cat, you have both, right? So there's 4 different groups there. Well, instead of using the qualitative response, we'll kind of assign each one of those responses or each one of those outcomes with a number, right? So I think I mentioned this a little bit when we were talking about this, qualitative variables at the very beginning of the semester, that you really can turn them into discrete random variables by simply assigning numbers to the different qualitative responses, okay? Nothing too crazy yet. So from there, we're going to be interested in something called the we're going to be interested in the probability distribution, right? So I have this experiment. I don't know what, I might know what all the possible outcomes are, but I don't know what outcome I'm going to see. So if I'm choosing a family at random, asking the number of kids in the household, I know I'm going to see 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 20 or whatever, right? But I also know that different outcomes are way more likely, right? The probability if I select a household at random that they responded, they have 1 child in the household, way higher than the probability they have 15, right? So I know that these different outcomes have different likelihoods of occurring, okay? So what might I want to see? I might want to see, okay, across all these different outcomes, what are the different probabilities associated with each one of these outcomes, okay? So in order to figure that out, we're going to need what we call this probability mass function. So P subscript, or I'll kind of show you different ways of thinking about it, but generally we notate it with, here's this probability mass function that tells me the probability of different outcomes for this random variable X. You know, you can think about it as, it could actually just be a function of like any function, right? Y equals mx plus b or whatever it is. But sometimes we won't even have a functional form. It'll actually even be a little bit easier than that, right? So the one that we'll start out with, the probability mass function, won't look like an actual function that you might see in a math class. It's actually just going to be directly told to us something like this, right? So maybe if we think about the number of children in a household example, as simple as my probability mass function could be, is something like, well, if I selected a house at random, I don't know, maybe there's a 0.4 chance they don't have any children, 0.2 chance they have 1 child, 0.15 they have 2, 0.05 they have 3, etc. I don't know if these actually line up with what the probabilities are, but we'll think that they are for now. So here, this is my probability mass function. It's just a schedule that tells me for different outcomes, right, for different number of children, what are the associated probabilities, or what's the probability this random variable X, number of children in the household, is equal to 0.4. What's the probability this random variable X, the number of children in the household, is equal to 1.2, right? And then kind of so on and so forth. So this could be as simple as your probability mass function is. It's just going to be directly given to you. Now, later today, and then Monday, we'll kind of look at, finish our discussion and introduce one more different type. We're going to talk about 2 very specific types of discrete random variables before we kind of wrap things up here. But for now, it could be as simple as this. Okay. So our probability mass function has to be between what? So when I plug in any value for this outcome, the probability associated with it should be between what 2 values? If it's a probability, the lowest probability it could ever be is 0. It can't happen. The highest probability would be a very uninteresting example, which is that you know what the outcome is going to be, right? The outcome, there's only one outcome you will see, and the probability associated with it is 1. It's guaranteed to happen. Now, we don't generally see that, so usually the probabilities are somewhere in between those values. So, you know, once we think about this, we would have all these XY pairs, right? I have all these different outcomes for X and all their associated probabilities. We could go back to graphing this, just like we did relative frequencies, right? Remember, relative frequencies, we just took that frequency and divided by the total number of observations. And we said we could then use those as our Y values and get kind of a nice, oops, sorry, I jumped the gun, and get this kind of nice, let me see if I got a picture here. we'll come back to it. I get this nice probability distribution, right? I've got these different outcomes I can see X take on, and I have the probability associated with each one of them. So we'll come back to that in a second. So I already said that the probability has to be somewhere between 0 and 1, but just like with relative frequencies, if I took the probability of every single possible outcome, these should add up to what? If I think about having like an entire experimental outcome space, it might be something like, well, here is what represents the probability of having 0 children. Well, actually, I should draw this so that it looks closer to the numbers that I have here. I'm sorry. 4. This is 0 children. Maybe here's the probability that I see 1 child. Here's the probability I see 2. Here's the probability I see 3, 4, so on and so forth. If I add up the probability of every single possible number of children, those should just add up to 1, right? The entire experimental outcome space. And the reason why is because these discrete random variables, when I run this experiment, I'm only going to see one value. I can't see a household have exactly 2 children and exactly 4, right? There's only going to be one recorded response. So essentially, everything is mutually exclusive here. I'm only seeing one response for this discrete random variable. It's only going to take on one value. So when I take the probability of every single possible value it could be, those have to add up to 1. It has to fill up my entire experimental outcome space. I didn't finish it here, but you can imagine like goes up to whatever the Duggars or whatever the largest family is, and they just get smaller and smaller. Any questions up to this point? Okay with this? Kind of review, because we kind of already did this with relative frequencies. Just like with relative frequencies, we can also start thinking about cumulative mass functions. So the idea of cumulative just meaning, remember, cumulative GPA. What's your GPA for this semester all the way back to the beginning of time, right? So what that means for us is what's the probability that I see a certain value for X or anything below it, right? What's the probability that I see a household have 3 children or fewer, okay? So my cumulative mass function, as that X value gets higher and higher, my cumulative mass function should be approaching what value? Yeah, I see someone holding their finger up, right? 1. You know, if I plug in 20 here, and I'm using the number of children example, what's the probability if I select a household that randomly have less than or equal to 20 children? I hope that it's 1, right? I hope there's no families that have more than 20 children, right? So the idea is as you approach these higher and higher X values, your cumulative mass function gets closer and closer to 1. As I get really close to the small values, my cumulative mass function should be getting closer and closer to 0, right? So I've kind of got, you know, both those directions. If I get, you know, smaller values of X, my cumulative mass function should be close to 0. Higher values, it should be approaching 1. And we won't really do too much with this today. Maybe at the end, I'll kind of relate something to this, but I've got some, I think, are fun examples I might replace that with instead. We'll definitely talk about this on Monday. Okay? So I have this example. We'll kind of set up some different things we can do with a discrete random variable. So I've got some company, I've got some historical data, I've got the last 35 years, the number of new hires they had every year. So there was never a year where they hired no one. So there's some turnover at this company, but they've also never kind of hired double digits, right? And maybe the reason why I would go up to 12 here is because maybe there's 12 positions at the company. So I know that a possible outcome could be that all 12 people are replaced, right? Now that's never happened before when I actually look at the data and I assign these probabilities empirically, but it is a possible outcome, right? So I've got all these different outcomes, the number of times they've happened over the last 35 years. How could I turn these into probabilities? So just like with our contingency table, remember we started out finding the frequencies? Yeah.
You put 1 equals 2, 2 equals 1, for like the P of X equals F of X. Is that what you were doing with that?
Yeah, so for the first one, I would say, okay, what's the probability that X is equal to 0, right? Well, the probability X is equal to 0 here would be what? There were 0 instances out of the last 35 years. So 0 over 35 would be 0. What about the probability that I see 1 higher? There I had 2 years where that happened out of 35, so just 2 out of 35. So basically, it's kind of like when we did our relative frequencies, we divided by the total number of observations. Here, I'm just going to divide my frequencies by the total number of data points I have, right? So it's still like the number of observations, but it's whatever, my data set starts out. So yeah.
So do you just go down the line and do it?
Yeah.
Set it equal to 35?
Yep. So I would just take each one of these frequencies, divide it by 35, and I can come up with the probability of seeing each one of these possible responses. Now, it could be that like, you don't have to empirically assign the probabilities. Like maybe this is something like you don't have any historical data. We might have to use the subjective method or class. But more often than not, we're going to be assigning these probabilities using some historical data or empirically assigning these probabilities, kind of like we would here. Now my Zoom thing is hiding this up. Like if I add these probabilities up, what should they add up to? Well, if I add the frequencies up, right, the numerator should all add up to the total number of observations. I was dividing everything by the total number of observations. I should get 1 there. Okay. So I've got these different possible X outcomes. I've got associated probabilities. How could I find? Oh, sorry, I jumped in. We can graph these. It's not that interesting. We've already done this, right? I could take my outcome of 0, draw a bar up to its probability. Well, it's probably going to 0, so that's easy. Then go to the next outcome, 1 on the x-axis, draw a bar up to its probability of 0.06. Do this for every single outcome. I can then kind of quickly see, 3 and 4 hires are the most common outcomes. The middle part of this data, I probably should expect somewhere around 4 or 5 hires. If I'm just roughly looking at this. I should never expect double-digit hires, and I should never expect there to be 0 hires, based off of kind of the history. So what might be more, I said, kind of the middle part of this data, right? We still might want measures of central tendency, now not just for a variable, but for some random variable, right? Where we don't know the outcome. We want to try to predict the future. Where should we expect this value to be? Okay. So I'll go. Let's add 2 examples. I'll work with this one first. So let's say another term that we kind of use for this now, mean of a discrete random variable, is the expected value because it hasn't happened. We're trying to predict what the outcome is going to be in the future. So if I go back here and I look at the original data, there's these different outcomes for X and their associated probabilities. What was I doing with weighted means? We said we'll take the sum of the weights times the X value for every single group, right? We were using that for group data. And then to divide by the sum of the weights. But here, if I wanted to find the mean number of hires here, well, my X value would kind of just be these different outcomes for the number of hires. What could I use as my weights? Well, if certain outcomes are more likely to occur, I can actually just use the probabilities associated with seeing those outcomes. So my probabilities are my weights. Okay. Well, that makes my life a little bit easier because now, and remember all these summation signs ever mean, technically I'm not writing them out notationally correct. I should always be putting this. Starting with the first, going to the last, I'm going to add up the probability of every possible outcome for X, right? So X1 would be 0, X2 would be seeing 1 higher, so on and so forth. So what should the sum of those probabilities be? We already said, should be 1. So what can I do? Ignore the denominator. If I divide by 1, it doesn't change anything. So really the mean of a discrete random variable is a weighted mean, but easier. Right? Kind of like we did like the one where we have the midpoint, we're using the histogram data. Yeah, returning to the probabilities, our life becomes quite a bit easier. So in practice, how would I find this mean? I just go through. Right? Here I've got I think prettier, here I've got kind of a complete thing here. Right? The sum of those weights is equal to 1, so we're just left with this equation for the mean of a discrete random variable. So if I'm looking back at that data, let me see if I have it. Here we go. What's the very first thing I'm going to do? I'm going to go look at that very first outcome for X. The first outcome I can see is 0 times the probability that I see X take on that value of 0, which here is just 0. That was not very interesting, right? I'll then go to my next possible outcome of 1, multiply that by the probability I see X take on the value of 1, which is what? 0.06. And then I'm going to go through and do that for every single possible outcome that I have up here. So it's going to be a little bit lengthy, right? But you can imagine in Excel, even if I had 100 different possible outcomes, which is very likely for these discrete random variable examples, well, I could just create another column where I take the X value, multiply by the probability, and then use that sum function to add that new column. Now by hand, it might take a little bit longer to do if I actually have to go through 100 different possible outcomes, which is why on exams like that, I'll generally give you these discrete random variables with 4 or 5 outcomes. And it makes it a little bit, you don't have to waste that some time. So I think we get off 5.14. So any questions over this process? It really should be reviewed. I mean, it's basically just a weighted mean where we don't have to worry about the denominator. So we get the average number of hires is about 5, right? 5.14. So the variance for a discrete random variable is going to look very similar to the weighted variance, except once again, our denominator goes away because the sum of our weights, the sum of our probability should always be 1. So all we have to do for the weighted variance, take each possible outcome for X, subtract the mean that we found, square that deviation, and then multiply it by its weight. Here our weight is the probability we saw that specific outcome or that specific value for X. Do that for every single outcome, add them all up, we've got our variance. Right? So once again, it's kind of like the weighted variance, but actually easier. We don't have to worry about the denominator. Right? Because the sum of our probabilities will always be 1. And then, just like always, if I want the standard deviation, I'll take my variance and just take the square root. Okay, so that's all that's saying at the bottom. So same kind of thing that we've been doing. Okay? So here's it all written out. It's a little bit nasty and ugly, especially when we have 12 different outcomes. But if we know the mean is 5.14, the first thing we'll do is we'll take the outcome of 0. We'll subtract that mean of 5.14, square that deviation from the mean, and then multiply by the probability we see that deviation. Right? We said the variance, even a weighted variance, is kind of the average deviation from this middle point. Well, this very first outcome, if it never can happen, then it shouldn't add anything to the variance, right? It's evidence that, well, yeah, the outcome never varies from the mean, right? Because you can't see 0. So, that's one outcome that's evidence there's no variation. Now, the other outcomes, right, are non-zero, so they do provide that there is evidence of some deviation from that middle point. We'll then add them all up, and we should be getting kind of this average deviation from the middle part or from that mean of this discrete random variable. So the process is the exact same as what we did with the weighted variance. It's just we no longer have that denominator. What's the lowest possible value this variance could be? Zero, right? That wouldn't be a very interesting example. That would be like the number of new hires that every single year this company has always hired exactly 2 people, right? So it's guaranteed based on the historical data to hire 2 people this year. There's no variation in the outcome. It's not very likely, but it's possible. So I want to maybe show a different application of this, and it is a lot more simple. But hopefully it highlights why we want to use these probabilities as our weights. So let's say I made some investment, and I want to choose values I can work with pretty easily. Okay. And here are let's say there's only 2 possible returns I could see. All right. A little bit of a goofy example, but let's say I make some investment and I'm either going to lose 10% or I'm going to gain 5% in this investment. So the only 2 possible outcomes, maybe it hinges on something happening with the market that either provides a slight increase or potentially a slightly larger decrease. Okay. I then am told, okay, the probability that you see these different outcomes for X, something like, what did I have here? This. There's a 10% chance that I see a negative 10% return, 90% chance I get a 5% return. Well, if I just treat this like a regular mean, and I said, well, okay, what's the expected value of this investment? Well, if I just add these up and divide by 2, right, I would get what? Negative 2.5. So I would think, yeah, I shouldn't make this investment. Right? I'm going to lose money. However, the chances that I lose 10% is much lower than I gain 5. So to get the expected return, what would I want to do? Well, essentially, I want to go through each one of these outcomes, take the outcome for X, multiply by its associated probability, and then add them up. So if I do that here, I get what? -1, -10 times 0.1 is -1, 5 times 0.9, 4.5, add them all up. If I factor in that seeing a return rate of 5% is a much more likely outcome, then the expected return of this investment is actually 3.5, right? So there's actually an expected positive return on this investment. So treating this, taking into account those probabilities completely switches my decision about whether or not I invest into this product or stock or whatever it is. So I don't know if how many of you take, how high you are in finance classes or whatever, but I'm sure maybe you're doing like expected values of or expected rates of return or expected rates of return on portfolios, kind of a similar idea. Okay. Any questions on this? So there's one other thing, and then these examples seem kind of trivial, but I think most often they're used in this context of predicting expected rates of return on investments. But it's not just the expected value of return. We could actually do this even a little more extreme. So let's say instead, I did something like this. All right, so now if I take my X value, multiply by my associated probability, I get what? Still -1 here, right? 1% of -100 is -1. 99% of 5, I'm going to kind of roughly estimate it here. It's like 4.9 something. I don't know exactly what the decimals are there, right? Add these up and I get a higher expected rate of return. So if I were to ask you which one of these investments was better and you look at the mean, you might say, well, that second investment. However, what is true about that second investment? Well, even though the probability is small, there's this one outcome that varies a lot from that mean, right? So I might also want to get a measure of variance for these investments because one of these is a lot more risky, right? And that variance would tell me which of these investments is riskier. Even though this second investment provides a higher rate of return, we calculate the variances, I can guarantee you, -100, even though it has a small likelihood of occurring, it's so far away from that mean. When I square that deviation, it's going to be a very large number times 1%. It's still going to be a very large number. So we then can use kind of these variance measures to kind of differentiate between which investments are more risky. Right, so you might see that kind of applied in some of the classes. So I want to have you guys work a little bit on these, kind of make sure you're kind of you're understanding kind of what I'm talking about. Also, a little bit of review of kind of calculating these weighted variances. So I'll give you a little bit of time, kind of work on these, talk to the people around you. Let's say I've got this kind of goofy example for a second, but let's say there's some huge company and this individual has possibilities of these different bonus amounts. I said they're in millions. You could say they're in thousands, whatever makes more sense. But they either get a $0 bonus, 3 million or 3,000, whatever you want to think about that, 6 million or $10 million. Right? So there's 4 possible outcomes for X. Each of them have different associated probabilities. I'll give you a little bit of time to hopefully come up with what the mean of this discrete random variable would be. All right. So you're looking for that mean of the bonus amount of this X variable, right? Where these 4 different outcomes have different associated probabilities of occurring. Like I said, talk to the people around you. They might know something you don't. You might know something they don't. Let's give you 30 seconds here and then we'll kind of talk about it. All right. If you haven't gotten an answer in, take your best guess. You guys having problems? Or you're just trying to figure out what the right answer is. All right. All right. So get everybody with a response, and I think count 18. All right. So before we even get into how we would solve this, think about what we're trying to calculate. We're trying to calculate the middle part of our data or the middle part of these outcomes, right? We have 4 possible outcomes, right? However, we know that which one is going to influence the mean the most, the one that's the most likely. So we know that 3 is going to influence the mean a lot more than some of these other values like 10 that are less likely. Okay? If I was a betting man, right, and I'm just trying to rule some of these answers out and I just have to guess, I can't write anything down, I can't even use my head to do the math, and I look at this and say, well, look, the 2 most likely outcomes are 3 and 6. And on either side of those, 0 and 10 are kind of close to equally as likely. They're both kind of far away from like the middle of these values. If I had to guess, the mean's probably going to be somewhere within 3 and 6 million, or 3 and 6 here. So, you know, what would have to be true if A and B was the mean of this discrete random variable? What would have to be true about those probabilities?
You have to have a higher probability of 0.
Yeah, 0 or maybe 3 gets a little bit more likely, but 0 and 3 would have to be like the only 2 likely outcomes. These would have to have a 0.01, you know, probability of occurring, because these will pull the mean up, right? And they have pretty substantial probabilities. So to be as low as A or B, I'd have to have 0 being really likely, probably a probability of 0.7, 0.8, if I'm just roughly guessing, right? So now I've got a 50-50 shot, right? I can guess either C or D. Well, from there, there's nothing I can really rule out. But the process I'll go through and do is I'll take every single possible outcome, multiply by the associated probability, and add them up. So one easy way to do this, you don't have to enter it in your calculator all at once. 10 times 0.15, or that x value times the probability this random variable x takes on that specific x value. 10 times 0.5 would be 1.5. 6 times 0.25, 1.5. 3 times 0.4, 1.2. 0 times 0.2, 0. Add them all up. I've got the mean of my discrete random variable. Any questions on that sort of thing? Everybody got that right?
So you don't divide by a number.
There's nothing to divide by, right?
No.
I said that before, right? Twice. We don't have to worry about the denominator. We don't have to worry about the denominator. Even if you wanted to, right? So if you wanted to divide by something, you're not dividing by the number of possible outcomes. You would be dividing by the sum of your probabilities. What do these probabilities add up to? 1. Yep. Any other questions on that? I'll get a couple of moments. So I won't ask you to kind of go through and calculate this one by hand. What I actually want you to do here to make sure you've been paying attention to a little bit of what I'm saying. I want you to respond with which of these answers, and don't respond verbally. I want you to respond to your eye clickers. Which of these answers can you for sure say is not the variance of this discrete random variable? I won't give you too long to think about this one. I want to kind of like a quick reaction. And hopefully if you've been listening, this should be pretty easy. Which of the following responses cannot be the variance of this discrete random variable? Okay. So a couple more of you still need to get in here. So make sure you get an answer in. Which of these responses cannot be the variance of this discrete random variable? All right. Make sure you get a response in. I thought there was 18 of us. Everybody make sure they. All right, there we go. Close it out. So hopefully this was not too bad. Which of these cannot be the variance? Yeah, B, right? Hopefully. I'm afraid to look at this.
Because then your variance.
Could be possible that the variance and the mean are the same value.
Right, based on our data, wouldn't that be impossible? Because there's.
I'm just saying which of these for sure cannot be the variance. You could actually have an example, especially if I'm choosing the numbers. I could very easily choose numbers where the variance and the mean end up being the exact same thing. All right. So think about. I think this would work. So. No, I would need something like 0 and 1, where the mean is 0.5, each one would be 0.5 away. I could actually end up with a mean that's the exact same as my variance. Right? I know for sure variances cannot be negative, right? But there's none of these other ones I can technically rule out. Now, once I calculate it, I can rule them out. But you can have the same mean as your variance. It'd be very unlikely with actual data. But if I just have a small set of numbers like this, where I've got maybe subjective probabilities, very possible you could just, the numbers could work out to where the mean and the variance are the same. Very unlikely. I'd agree with you. Like, if I'm a betting man, I probably don't think that that's going to happen, right? But the only one I can rule out just by looking at this data would be B, right? So hopefully, okay, well, almost everybody got that one, right? So we cannot have negative variances, right? Trying to hammer these principles down so when it comes to the exam, it makes it very easy. You can rule out some of these answers, prevent yourself from making a really easy mistake. Okay? So why can't I have a negative variance? We said the lowest the variance could ever be is 0. Okay? Now, it would be very unlikely the mean and the variance end up being the same value. So if we remember that the mean was 4.2, if I'm looking at this, I mean, it seems odd that the variance would be the exact same. 1.9 seems pretty low, simply because, you know, if I'm thinking about 10 would be almost 6 away from the mean. 6 squared, right? We would take the deviation squared, 36 times 0.15. Seems like 1.8 is probably a little low if I'm just eyeballing it, but theoretically I can't rule it out, right? And it's a little bit hard to visualize what the value of the variance is going to be. So I probably just have to go through and calculate this by hand. So the very first thing I would do, and you can kind of do a similar thing like you did for the mean. You could create just another column, right? So, you know, I don't take the first one, the x value of 10 minus the mean of 4.2. So what? 5.8 squared times 0.15, write that number down. Then go to the next outcome, 6 minus the mean, right? That's what? 1.8 squared times the probability you saw that, write that number down. Do that for every single observation. And then add them all up. That way you don't have to enter it all into your calculator at once, worrying about your parentheses, especially if I'm giving you a very similar example like this on the exam. You only got a few outcomes, you kind of create this additional column. I think it might make it a little bit easier to kind of break that up into parts, all right? I have to re-click on my slides to get this to work, which is annoying. All right. I don't think I actually have that up here. So just in case you're kind of curious about what that looks like. All we would do there is 10 minus the mean squared. All right, take the deviation of that first outcome for x from the mean, square it, multiply it by probably that x value occurs. Do that for the next possible x value of 6, square that deviation, multiply it by the probability that occurs, and then we'll just go through just in case you want kind of a complete work through of this problem. If my explanation up to this point hasn't allowed you to kind of foresee that, you know, or see that that's what it would be. This is be what you enter into your calculator all at once. Like I said, it's kind of tricky if you forget parentheses, something go wrong, which is sometimes why I just kind of suggest create this new column, break it down into parts, and then add them all up. Any questions on that before we keep moving? Kind of wraps up this topic, and we're going to jump into the next one. Okay with this? All right, so I think the next one, first of all, a little bit of an aside. Does anybody recognize what these stills are from? Yeah, so as business students, if you guys haven't seen The Big Short, I highly would recommend it. First of all, because it's actually a very educational film. It'll allow you to understand, I think it puts like in a really easy, digestible way, what happened with the 2008, 2009 kind of mortgage-backed bonds crisis, why the economy took such a hit when that occurred. And they do it in a way that, I mean, I always tell people, like, first of all, it's a pretty good movie, entertaining, but it does explain in a very non-detailed, but like easy, digestible way. I always tell people my sister, who is like the most bohemian hippie you can ever imagine, watched the film and actually could have a discussion with me about what happened and like enjoyed it. I mean, she talks about crystals and stuff. So like, this is the outside of her realm of things she would like. So it's a really good movie. It's a really good way to understand what happened without getting like a really boring lecture about it. So if I was teaching like a macro course, I would just have you watch the movie instead of teach that. So anyways, I digress. So the next topic we're going to look at is a very specific type of discrete random variable. Okay, so I kind of showed you these general ones, and they kind of apply when you're thinking about like investments or things that are probably have subjective probabilities. But more likely, or what's more interesting examples are these binomial setups, right? So if we have a discrete random variable that we know has a binomial distribution, to calculate the probability, of a certain number of successes, we actually have a nice functional form. So it'll make a little more sense in just a second. So the setups for a binomial distribution example would be if you have an experiment and you're running it over and over and over again. This could be as simple as flipping a coin. I'm going to flip a coin, say 100 times. Okay. My number of trials there would be 100. I've got an experiment flipping a coin. I don't know what the outcome is going to be. I'm either going to see heads or tails, but I don't know what I'm going to see until I actually flip the coin, and then I can record that. I'm also going to have that. I have to have like a binary response to this experiment. I'm either going to see what I define as a success or a failure, right? If you think of the two outcomes, it would have to be complements, right? I either see heads or I see tails when I flip this coin. If I roll, what would be another one I can think about? If I'm selecting somebody at random, maybe I'm interested in whether or not they have blue eyes, right? So there, they either have blue eyes or they have some other color of eyes, right? So these success failures, it's not like they're always failures or successes. It could just be whatever we're defining as a success, really whatever we're looking for. So it could be as simple as, does the person have blue eyes? We then have to have on any one trial, the probability of success is the same. So for instance, if I flip a coin, every time I flip that coin, the probability I get a heads is 0.5, right? Doesn't matter if I flip it 50 times or 100 times, each of those 100 coin flips, every single individual flip, the probability I get a heads is 0.5. If I'm selecting someone at random, the probability of whether or not they have blue eyes, maybe I look at historical data over the entire population, and I know that on average, the probability somebody has blue eyes is 15%. Or if I selected one person at random, the likelihood they have blue eyes is 0.15. That's the kind of idea there. We also have to have the trials are independent. So I'm never going to try to trick you with this. All the examples we're thinking about where we have successes and failures, the underlying probability of success, I'll usually throw in a statement that the trials are independent. But in practice, usually, I mean, we've identified that we have kind of this binomial setup from the other three characteristics. Not very likely that the trials are not going to be independent. So the idea of independence, right, is that it doesn't matter what happened on the previous 15 runs of this experiment. The 16th time I do it, the underlying probability of success hasn't changed. So that's why a coin flip is a really good example. I could flip a coin 100 times. Let's say the first 10 times I get heads. What's the probability on the 11th coin flip I see heads? Hasn't changed at all, right? The previous outcomes of this experiment don't influence future outcomes. So then what we're looking for, the random variable X that we're interested in every single binomial example, you can almost think about it as I'm looking for the probability of a certain number of successes. Now, the way that we'll write this is the probability X, this random variable X, is equal to some, some value for us. So the probability of the number of successes we see is 10. The probability of the number of successes we see is 35, right? but the random variable X we're interested in is the number of successes. So my example would be if I flip a coin 100 times, I want to use this binomial distribution to figure out what's the probability that I see out of those 100 coin flips, 40 of them come up heads. Because I know on average, like intuitively, if I flip a coin 100 times, what's the most common number of heads I'll get? 50, right? But on any given 100 coin flips, I could see 45 come up heads. I could see 63 come up, right? And any, if I flip a coin, maybe it's easier to think about 10 times. It's very possible I could see 8 or 9 of them come up heads. Right? Not the most likely outcome, but it is possible. It has a non-zero probability of occurring. Okay? So we have an actual function that will tell us the probability that the number of successes is equal to a specific amount. Okay. So even though I know 50 is the most likely outcome, I could find the probability of any number of heads 0 to 100. Okay. So the function that's going to give that to us is a little nasty, right? But I'll kind of break this down. It's not as bad once we start working with it. So hopefully, once we identify what the different components are, we'll see that this isn't too bad. So X is just going to be the number of successes that we're interested in finding the probability of. So what's the probability that we see 5 out of 10 coin flips come up heads? X would be 5. I'm skipping this one for a second. And it's just going to be the number of trials, right? How many times are we running this experiment? Well, I'm flipping the coin 10 times. The underlying probability of success, P, right, for a coin flip example would be 0.5. If I use my eye color example, the probability of success there would have been 0.15, right? Any one person, probably any one person that blue eyes was 15%. So once I have those, I'll always be given those 3 things, or I'll always know those 3 things. Then it's just a matter of plugging them into this formula. Now, I think hopefully we can put things in our calculator where we take things to a certain power. That's not too bad. You've probably done that before. Once I have like these guys and multiply them, the hard part of this equation is this fraction, right? So that exclamation point in math is called a factorial. So does anybody know what a factorial means? You can say it in the most non-technical way if you've ever seen it. Nobody's seen this before? It's okay if you haven't, so I'm not necessarily expecting. Occasionally I'll get someone that knows. If I have 10 factorial, so I've got n factorial, right? N is going to be some number. Whatever is to the left of this factorial, this exclamation point, I'm going to start with that number and just multiply all the way down, if I don't run out of room, to 1. So all that factorial means, start with that number and multiply all the way down to 1. Now, technically, you can write this out like this, right? Start with that number, multiply by that number minus 1, multiply by that number minus 2, so on and so forth. But the easier way to think about it is start with that number and just multiply down to 1. Okay. So now that we know how to kind of calculate those factorials, the only other thing that we need to know in some of these examples we're looking at is that 0 factorial ends up being equal to 1. Okay. We won't dive too deep into why that is. It looks a little counterintuitive. But for the sake of this class, we just need to know 0 factorial is equal to 1. Okay. So we'll start working with some actual values and we'll kind of see how this plays out. And I'll show you some things that we might make life a little easier, but also things that we might want to look out for. Okay. So first example we have was something like this. So I'm going to have an example where I flip a coin 10 times. It's a biased coin, so the probability that comes up heads is not 0.5, but instead 0.4. What's the probability 4 out of those 10 coin flips come up heads? Well, I know that it's going to be a pretty likely outcome, right? In fact, I'm jumping the gun a little bit, and probably won't talk about it today, but the next class I'll kind of reaffirm. Here, if I wanted the mean for my random variable X, or the expected number of successes, if I flip a coin 10 times, and the probability in any one flip I get heads is 0.4, what do you think is the most common number of heads I would get in 10 coin flips? So I flip the coin 10 times, probably any one time I flip it, it comes up as 0.4. Out of those 10 coin flips, the most common number of heads that I get would be 4. If I flipped it 100 times, and let's say it was an even fair coin, probably I get heads 0.5. You said earlier the number of expected coin flips, the most common outcome would have been 50. How was I doing that? I was really just taking the number of coin flips or the number of trials multiplied by the probability of success. Now it's easy to kind of visualize when we have numbers like 10 and 100, we have numbers like 34, so it's a little bit harder to kind of do the math in our head about what that mean is. But that's all, you know, this is, I think, somewhat intuitive, even though it does actually follow a kind of formula here, right? So the mean of a discrete random variable that's binomial, take the number of trials and multiply by the probability of success. So even though I know this is the most likely outcome, how likely is it? What is the probability that this random variable x, the number of heads I get in these 10 coin flips, is equal to 4? So I've already kind of identified this, but my x value is 4. I'm flipping my coin 10 times, so that's my number of trials. And it's a biased coin where the probability of success, or the probability of heads, is 0.4. From here, it's just a matter of plugging these 3 values into my binomial formula. So I've got the general form. Everywhere I see an n, I'll plug in a 10. Everywhere I see x, I plug in 4. Everywhere I see p, I plug in 0.4. Once I have it written out in the context of my example, I can make this a little bit easier. So I'll kind of give you an idea. So first of all, as I'm kind of writing this out, this factorial, you actually probably have, no matter what, unless you have like a dollar store calculator, even pretty simple calculators will have a factorial button in them. I know like on the TI 80 pluses, anything above 80, it's usually second math, and then you have to go over, either says PROV or PRB, and then you go down, you can see the exclamation point. On a lot of the other calculators, you have to hit the second button, and then there's like an option where it's either PRB or math, and then you usually can find it under there. Before the exam, you need to know where that factorial is at. And I'll show you that. I guess technically you don't have to, but it will make your life a little bit easier. If you can't find it, there's 2 steps. First, Google your type of calculator factorial button. It probably will help you find it. If you can't find it, let me know. I'll probably first Google your type of calculator and factorial button and then tell you what I find, right? I don't have all the calculators memorized. So that'd be, you know, but even if you can't find it in Google, I'm sure I can kind of after class or something, play around with your calculator and figure out where it's at. Like I said, for most of those TIs, right, it'll be second and then math, and then there'll be a kind of probability option. But we don't need that for today, okay? We can actually do this by hand without needing a factorial button on a calculator, okay? So I'll kind of break down how we can do this, right? So first of all, what I would do, instead of trying to enter this into my calculator all at once, break it down to pieces because the order of operations will get tough, right? So all I'm going to do first is figure out what 0.4 to the 4th is, write that number down. I'm going to do the math that I can do in my head first, right? So this is just 1 minus 0.4, 0.6, the 10 minus 4, the 6. Put that in my calculator, write that number down. Right? I'm just simplifying things down, breaking it down into steps, you know, so that when I multiply this by 0.4, I don't take the whole thing to the 4th power. The last thing that we're going to have to do, and this should be easy, right? Hopefully we can take things to powers. This is going to be a little more difficult, right? Well, the first thing I'm going to do is I'm going to simplify this. 10 minus 4 is what? Yeah, so why mess around with all these parentheses, right? So instead of entering this in my calculator using that factorial button, or maybe I can't find it today, what I could do is just write it out, and hopefully it'll allow us to see this is actually a little bit easier to do by hand than we might think. Right? So I wrote out 10 factorial, I wrote out 4 factorial, now I'll write out 6 factorial. Well, notice, how can I simplify this? Everything past 6 cancels. All right. So That's going to apply to no matter what values I have up here. I'm going to be able to cancel quite a bit of what's in my numerator and my denominator. Now I can very easily in my calculator 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. Then I'll have my 3 components, multiply those by each other. I can come up with the correct. Like I said, you can do this all in your calculator in one line. It's easier to make mistakes. So why this works is a really nasty, boring proof that we're not going to go through. For our sake, we just know that this formula will give us the accurate probabilities. You can prove this to yourself, like with data, like if you do 100 coin flips, you can like simulate stuff and then use this formula, and you'll see that the simulation matches up perfectly with the probability of the formula will tell you. Any questions about what I'm doing there with the factorials and kind of canceling? Is that kind of clear? I'll give you another example where you might think that it's not even possible to calculate something. So let's say I had another example, where my n was 100, my x was 2. So I don't know. 100. No, sorry, this would be to 2 times 1 minus 0.4 to the 100 minus 2. We'll kind of ignore this because hopefully we can take things to powers. I'm really going to focus on how can we simplify this component, right? So if you try, did anyone find the factorial button on their calculator? You try to type in 100 factorial, what happens? If anybody found it. Nobody? Yeah, you can't do it, right? Your calculator is like, it's way too big. 100 times 99 times 98 times, that gets to be a really large number. Your calculator can't store it. So this is a really good example where, and this can happen on computers too, where you enter something in, Excel might tell you it can't do something. Well, it's because the way in which it calculates it, it might not be able to deal with these intermediate values that are really large. But if you use your head, use your brain, we can simplify this to something we can actually do, right? So 100 factorial is just taking 100 and multiplying down to 1, divided by 2 factorial, so 2 times 1. And then this would be 98 factorial, so multiply that by 98 times 97, all the way down to 1. Well, notice everything here is going to cancel. All I'm left with is 100 times 99 divided by 2 times 1. I can get that entered in my calculator pretty easily, and then I don't have it telling me that it's an error. Okay. So I might do something like this occasionally on an exam, just to like see that you understand what's going on with factorials, and to prove this point that you can't always rely on technology and black box functions, because sometimes those black box functions will tell you it can't do something. Whereas if you simplify it first, it's just the mechanical procedure that it can't do. It can't store this value and then divide it by storing that value. And that's the way that your calculator works, right? But if you simplify things ahead of time for it, your calculator can definitely do that. Okay. Is that okay, clear what I'm getting at here? Okay with this? Where are we at in time here? I was gonna say, I bet we're right at about an hour. Okay. So, what do I want to do? So we get about 0.25 if you want to kind of work this out. I think I'll go through one more example and just kind of walk us through it. It's not going to make me crazy, and I think that has something that interesting. So let's say instead, let's say these coin flip examples. I know that 30% of people have a college or a 4-year degree. Right? So if I ask 5 people at random, or I select 5 people at random, excuse me, what's the probability that 3 of them have a college degree? Maybe I should preface, people over the age of 30 or something like that, so we're not sampling younger people who couldn't have. So here, what would my 3 things be? I need the number of trials, I need the probability of success on any one trial, and I need to know the number of successes I'm interested in finding the probability of. So what would my n be here? Yeah, I'm asking 5 people, or selecting 5 people at random. Here, the experiment is simply selecting a person at random. Kind of like select a person at random, ask them if they have blue eyes, or record if they have blue eyes. My underlying probability of success that any one person has a degree would be what? Yeah, 30% of people have a college degree. If I select one person at random, the probability they have a degree would just be 0.3. And then the number of successes I'm interested in finding the probability of, I wanted what? Probability that 3 of them have a college degree. 3 out of the 5. You can kind of think about it as X's. I'm interested in finding the probability of blank out of blank. All right. So I'm interested in finding the number of successes out of the number of trials, or X out of N. So 3 out of 5 people. Now it's just a matter of plugging in those values. If I go back to that general form of the equation, N is 5, X is 3, and minus X, so 5 minus 3. Probability of success is 0.3 to the X power times 1 minus that probability of success to the N minus X. So I'm just plugging my values in. Okay? So really what this becomes is just getting familiar and used to using this equation. So I might, I've got some questions I've been used for an online quiz. I'm using non-quiz for this. So I might put up a practice quiz on Canvas. It just has a couple problems that has some different values that you can kind of work through and try to kind of see if you can calculate the correct response there. So that way you just have more examples you can kind of work through. We'll probably work on a few more on Monday as well, but just to have some additional practice, I'll try to get those up there. Now, what I would do in practice here also is simplify everything before you even go to your calculator. So here, 5 minus 3, is 2, 1 minus 0.3, 0.7, 5 minus 3. Just do the math in your head if you can. Don't overcomplicate it by having to add more parentheses when you get to the calculator. But really, that's all we're doing. Just identifying those 3 components, plugging them into our formula, and then making sure we can send it to our calculator. Where are you going to put the formula to? It should already be up there, unless I originally had it under the files tab. It's a good question. I thought I showed this. I might have mentioned it, and I just probably mentioned it really fast. Under that exam 1 practice materials, I moved the formula sheet so that it's there with those practice exams. Yep. All right. Any other questions kind of on this binomial stuff? Got one more thing that I kind of want to show you here with the binomial and related to some stuff that we've already done. Okay. So let's say instead, I want to know what's the probability all 5 of these people have a college degree. Okay. So I'm going to write this out. Plug in my N and X values, and then discuss it here for a little bit. So N and X are the same thing. Right? I want to know what's the probability all of my trials are successes. Okay. Well, what is 5 minus 5? 0. Anything to the 0 power is what? Do we know this? Just 1, right? So anything to the 0 power is 1 there. So multiplying anything by 1, I essentially can just ignore that. Right? It doesn't change anything. What is 5 minus 5? Well, that's 0. 0 factorial is just 1. So I can essentially, if I'm multiplying or dividing by 1, I can ignore that. What's 5 factorial divided by 5 factorial? That cancels. This entire fraction is 1. I can ignore that. So if I want to know the probability that all of my trials are successes, the only thing I'm left with is that underlying, I don't have the general form written down, the underlying probability of success raised to whatever the highest possible number of successes is, in this case, 5 out of 5. Okay. So if I want to know the probability that all of them are successes, everything simplifies down. This is pretty easy to get entered into my calculator. Now, what that actually corresponds to, it's supported by things we've already talked about. So remember what I said with these binomial examples is that they have to be independent events. Okay. So what I'm really saying here is, what's the probability that the first person has a college degree, and the second person has a degree, and the third person has a degree. All right, so I want the intersection of all these things. Well, if they're independent events, we said that. I'm in another room here. Just when I have two, we kind of kept it simple. That one way I could check to see if they're independent, or one thing that should hold, is the intersection of the two events would just be each event multiplied by each other. That goes back to, we said there's three ways to check independence. We can check to see if the conditional and the unconditional probabilities are equal to each other. But this third way, if they are independent, we work the math out to show like this would have to hold. So if I want to find the intersection of all these things, all I have to do if they're independent is multiply the probability of each one by each other. So what's the probability the first person I select has a college degree? 0.3. What's the probability the second person I select has a college degree? 0.3. What about the third person, the fourth person, and the fifth person? 0.3 times itself 5 times. 0.3 is that. Right? So the fact that they are independent events, if we want to know the probability that all of the trials are successes, it goes back to really, we're finding the intersection of these events that are independent, so we can just multiply the probability of each event. We said the underlying probability of success is always the same, so it's that probability of success to whatever power kind of we're capped out at. I don't know the number of trials. Is that any questions on that? After that kind of makes sense a little bit. I do have one thing I want to show, but I want to make sure that we have plenty of time next week. So there's one more thing that I want to get at here. I think the next idea might be cumulative. If it is, I might skip around a little bit. Okay, it's not. So this is perfect. So let's instead say, I just want to kind of show you something we'll reuse next week. So here we can think about, here's the different number of people I could see have a college degree out of 5. Right? We just found in the previous slide, I believe it was the probability that there was 3. I think it was what? 0.13. Okay. Now it's a little bit trickier, and I had it written down earlier, but remember, how can we find the mean of these binomial variables? I said it was take the number of trials, multiply it by the probability of success. Now that's easy when I've got like 10 or 100, but if I have 5 people, here's another easy way to think about it. If I had 10 people, and the probability any one person has a college degree is 0.3, out of 10, what would be the most common, or what would be the expected value for the number of people that have a degree? Out of 10, it would just be, well, the probability that any one person has a degree is 0.3. 10 times 0.3 would just be 3. Right? But out of 5 people, well, that's half of 10. So my expected value should be half of whatever it was before, half of 3, 1.5. Now I could just plug my values in. I don't have to think about this in my head. 5 times 0.3. The most common response, or the mean of this binomial, would be 1.5. Now the problem is, in practice, I can't see half a person have a degree, right? But what this tells me is what will be the 2 most likely outcomes. 1 and 2, right? If I get a mean that's in between 2 of my integers, what that's really just telling me is my 2 most likely outcomes will be the integers on either side of this mean. And then as I move further from that mean, my probabilities should be decreasing. So this is the idea of, okay, if I flip a coin 100 times, the probability I get 50 out of 100 is pretty high. Actually, let's not do 100. Let's say I flip a coin 10 times. The most likely outcome would be I get 5 out of 10 heads. It's probably going to be a pretty high probability. But on any given 10 flips, I might get 6 heads, or I might get 7. But I know that the probability of getting 10 out of the 10 to come up heads is pretty low, right? And then as I move further away from that expected value of 5, getting 6 out of 10 heads isn't as likely as, getting 6 out of 10 heads is more likely than getting 7 out of 10, which is more likely than getting 8 out of 10, which is more likely than getting so on and so forth. So as I move further from that mean, the probability of these different number of successes starts to decrease, right? It'd be very unlikely I see all 5 out of 5 people I select have a college degree. Okay? So before, we found that the probability of 3 people having a degree was what, 0.13? What has to be true about the probability 4 people have a college degree? Has to be less. Well, the probability that we saw 3 has to be greater than the probability that we see 4. I guess you could say that in either direction, right? As we move further from that expected value of 1.5, the probability of these higher number of successes declines. Right? So the only possible value up here that's less than 0.3 is the 1.3 is 0.028. Now we can work this out. It'd be the same thing we had before. It's just now we replace the number of successes. Instead of 3, we'll have 4. We could rework that. And what we should come up with is that probability ends up being 0.028. Work through some more of this. We'll come back to this, but I have one more thing. I'll kind of use that law of independence. I think this is kind of interesting. I think it was earlier in the slides and I moved it around. But if I see, let's say someone's flipping a coin and it comes up heads 5 times in a row. The probability I get a heads on that 6 coin flip would be what? Still 0.5. Right? The previous outcomes are independent, so they don't influence the future probability. So no, if I see a long run of tails, it's not more likely I see a heads or tails in the future. Okay? So I actually ran through some simulations. I had like 10,000 coin flips, so just using random numbers in there in Excel. And every time there was exactly 1 tails, the next coin flip coming up heads, that probability was about 0.5. Every time in that simulated data I saw 2 tails in a row, the probability on the next flip I got a heads is still pretty much 0.5. 3 in a row, 4 in a row, probably I see heads really right around 0.5. So it doesn't matter the outcomes of the previous experiments. Underlying probability of success of independent events remains the same. Okay? So kind of an interesting example is there was this casino in France back in the early 1913, and they had this roulette table. For the sake, I don't know if any of you are gamblers, hopefully not. It's too easy to be with FanDuel and DraftKings now, but if you spin the wheel, there is a green space, but generally it's about 50% chance you see red, 50% chance you see black. We'll kind of simplify that for this example. So the probability of any one spin and it comes up black is 0.5. But what if I see it come up black 5 times in a row? What do you think most people probably do on that 6th spin? They bet red, even though the probability was the same as the previous 5 spins, right? So we call this the gambler's fallacy, right? You believe, because it's kind of correct in that, like, over 1 million spins, about 50% will be black, 50% will be red. But if you're looking at any small section of those 1 million spins, who knows? All bets are off. So there was this casino, and black actually ended up hitting 26 times in a row. So after about 8 or 9 times of coming up black, people started putting crazy amounts of money on red. But then on the 10th flip or 10th spin, it came up black again. Well, you got to get my money back. So on the 11th, it's got to come up red this time. Bet a bunch of money on red, comes up black again, right? So this casino made like an insane amount of money because people just kind of fell victim to this gambler's fallacy. In fact, kind of peruse the fan or the sports gambling apps, and they definitely are trying to get people with this. So I see them all the time. They put these, they're trying to bait you into, every time they set a line, it's always a 50-50 bet. Every bet you see on there, well, I should say, when you're talking about point spreads and over-unders, they've got some other things in the morning, but they should be 50-50 bets, right? But if you see that things start coming up, previous outcomes would be more likely or have been successful in the past, they start to make it like a more of an attractive kind of bet to you or start to advertise it for you, but it's still a 50-50 bet, right? They're kind of hoping you fall victim to this gambler's fallacy, right? And we see this play out in a lot of different ways. Kind of interesting example. I'll kind of leave it at that, let you guys get out of here. So I will see you guys on Monday. As you're working through those homeworks, if you have any questions, please reach out. Do not wait and try to accomplish them next Thursday or Friday. All right? Enjoy the weather, the fun, safe weekend. I'll see you guys on Monday.